Okay, today we'll start chapter 6. And like I mentioned last time, in chapter 6 and 7, we may slow down a little bit because these ideas may be newer. Okay, but let me start with the following. Probably the first time that you learned what a vector was a long time ago in some math or physics class was someone told you that a vector is something with a magnitude and a direction. Okay, so I also learned this back when I was young, like you all. Except this is a lie. Okay, so it's maybe true for vectors in Rn, right? So you can think of elements of Rn, you can visualize them geometrically, and to those vectors you can associate some direction and some magnitude. But there you're using something about Euclidean geometry. So you're using some Euclidean notion of length that relies on properties of R. And so OK over R. And maybe you can even make a notion of length of a complex vector because you have the notion of the magnitude of a vector in C. This is also really just using the Euclidean notion of length. But there's a lot more fields in the world other than just R and C. So if F is any field, you can always take a vector space over F. It's characterized by those axioms we talked about, right? That you have these elements where you can add them, you can scale and multiply them, and F has two operations, addition, multiplication, it has inverses, right? If you go back to those lectures on fields at the very beginning. So over arbitrary fields, over other fields F, you can have vector spaces, but not necessarily have notions of length or direction. In some vector spaces, it doesn't really make sense to talk about length because you don't have like the absolute value or the magnitude that you have in R or C. So really, the real definition of what a vector is a vector is an element of a vector space. Which seems not illuminating at all, right? Somehow it's not illuminating, but it's actually the only correct definition. Right, so we know exactly what a vector space is over a field. It's a set of elements where you can add and you can scale and multiply by elements of the field, and just any element of a vector space is a thing that you call a vector. Okay, so whoever lied to you, I'm sorry. I've now told you the truth about vectors. On the other hand, if we are in Rn or Cn, then vectors have such a natural notion of magnitude and direction and angle that if we study these properties, it should tell us more about Rn and Cn. Right, so you can always study vector spaces over any field. You don't need to consider a magnitude or a length to study vector spaces. But on the other hand, in Rn, or maybe even Cn, length and magnitude are just so natural. They're such natural notions that we must be able to learn something from them. Right, because when you think about R2 or R3, you draw pictures, you look at lengths, you look at angles. What we're going to study now in this chapter is inner product spaces. And inner product spaces are vector spaces that just have an extra structure called an inner product. And that extra structure will sort of be able to tell us about things like length and dimension in other vector spaces that aren't Rn or Cn, although they will be vector spaces over R and C. Okay, and this can be useful. For example, in quantum physics, what you study is you basically study Hilbert spaces, which are just vector spaces which admit an inner product and have some other properties. So special inner product spaces. Okay, so let's motivate with thinking about the Rn picture. So motivation, let's think about Rn. Okay, so first of all, in Rn, you have a very natural notion of length. So we'll call this the Euclidean norm of a vector. Or the length. So let's say our vector is x1 through xn in Rn. And what it is, so we'll denote it with these double bars. What you do is you just take the square root of the sum of the squares of each of the coordinates. Right, so this is, I mean, the two-dimensional picture or the three-dimensional picture is something you can sort of imagine. You have a vector here, it's some x1, x2. And then the way that you think about this thing's length is, here's the length of x1, here's the length of x2, and this thing has length, the square root of x1 squared plus x2 squared. That's the Pythagorean theorem. You just extend this naturally to any dimension. You look at a vector in Rn, you square each of its components, you add them up, you take the square root. That's what we call the length of a vector, or the Euclidean norm. Okay, but another way to think about this quantity here inside the square root is that this is just the dot product of x with itself. And so the dot product is just the one where you multiply coordinates and then you add them all together. But we haven't actually defined the dot product yet, so I guess I owe you the definition of a dot product. So the dot product of two vectors x, y in Rn is if you take the dot product of x and y, and let's just say what x and y are here. So x is x1 through xn, y is y1 through yn. The dot product is you take the first coordinate of x and the first coordinate of y, you multiply them together, you add it to the second coordinate times the second coordinate, up through the nth coordinate times the nth coordinate. So this is the usual dot product that you remember from calculus. Okay, so this is a product. It's only defined between two vectors that live in the same vector space. So, right, because you need to match up coordinates. You can't dot a vector in R2 with a vector in R3. But you can dot two vectors in R3. And just note that the dot product here, it's a product in the sense that it takes in two vectors in Rn and it spits out a scalar. Okay, so the dot product of two vectors is not a vector, as you know. Okay, so another way to say this is just that the dot product of x with itself is the square of the norm of the vector. So what this says is that this dot product somehow understands or knows about lengths of vectors in Rn. If you dot a vector with itself, it tells you the square of the length, so the dot product can tell you the length of a vector, essentially. But the dot product also has several other nice properties that we hopefully remember. So dot product properties. So first of all, if you dot a vector with itself, this number is always bigger than or equal to 0. Because, right, again, you're dotting x with, of course, if you're dotting two different vectors, then you could have a negative dot product. But if you're dotting the same vector with itself, you end up adding together a bunch of squares. These squares are all positive, or non-negative, I should say. Another property is that this equality holds if and only if x equals 0. So the only way to get two vectors to dot, or a vector to dot with itself to get 0 is if you take the 0 vector. Another way to say this is that the 0 vector is the only vector that has 0 length. which is sort of clear if you think about it geometrically, right? Here's maybe a less obvious property that you could prove. We'll actually prove something more general, I guess. No, we'll assume something more general, so maybe you should try to prove this. So for a fixed vector, so let's say you just fix a vector, I don't know, 1, 3, 2, right? Then you can define a map from Rn to R, which takes x to x dot y. Right, so I'm thinking of this function as you're plugging in different x's and you're dotting it always with the same vector, y, this fixed vector. Turns out that this map is linear. You should think about how to prove that. And then finally, the dot product is commutative. It's not so hard to see from the definition. X dot y equals y dot x for all x, y, and Rn. Okay, so these are the properties of the dot product. And what we'd like to do is we would like to somehow generalize the idea of a dot product even to vectors that live in crazy vector spaces. So the way that you generalize something is basically you look at the properties that you want and you just impose these properties. Although these are not exactly the properties that we're going to want. We'll see in a second. We're going to motivate further by looking at complex numbers, and we'll realize that we'll have to modify this a little bit. Okay, but the dot product, the reason that we want to generalize it is because the dot product knows about lengths, as we mentioned here, but the dot product also knows about angles. Right, so you may remember from Calc 3 that if you take the dot product of x and y, this is a scalar, and you can compute it by taking the length of x times the length of y times the cosine of the angle between them. Maybe you remember this. So what this says is that the dot product actually not only knows about lengths, the dot product also knows about angles somehow. So if we can generalize the dot product to something, again, more general that maybe applies in different spaces, or even just is a different kind of product on the same spaces, then we may get other notions of angle and length that may be useful for other reasons, right? Euclidean geometry is not the only kind of geometry out there in the world. It's like hyperbolic geometry, spherical geometry. So if we abstract these ideas, maybe we can get something new. Okay, but actually let's motivate further, because these are not exactly the properties we want. Let's think about Cn for a second. And when we're thinking about Cn, we'll realize that there's a little subtlety in these properties that we sort of miss because we're working over R. Okay, so recall that if lambda is a complex number, then you can write lambda as a plus bi, where a and b are real numbers. Then, first of all, there's a notion of the absolute value of a complex number. It's basically just, it's basically Euclidean length if you think of a complex number as an element of R2, right? But now our field is C. So it's like this is the one-dimensional vector space over C. But if you take an element of C, a plus bi, you call its length, its absolute value, this square root of a squared plus b squared. This is, of course, a real number. Because you've squared two real numbers, so you get something non-negative. You've added them, you have something non-negative. You take the square root, you get a real number. Okay, also the complex conjugate. Let's say the complex conjugate. Lambda is just the new complex number a minus bi. And then maybe a not necessarily so obvious fact, but easily checked, is that the square of the absolute value is the same thing as lambda times lambda bar. Right? This is just because a plus bi times a minus bi equals a squared plus b squared. Okay, so this is just basic properties of the complex numbers. But with these basic properties in place, then we can actually define a norm on Cn. So with these basics, a notion of length, let's say, on the vector space Cn, right? Because we have an absolute value on C, it's just the following. If Z1 through Zn, let's say this is a vector in C to the n, then I can define the norm of a vector Z as the square root of the length of Z1 squared, or the absolute value of Z1 squared, plus the absolute value of Zn squared. Okay, so here the thing to know is that the single bars, that's the notion of absolute value on the field, either R or F, sorry, R or C. Whereas the double bars, that's like you're taking the length of a vector in a vector space. Okay, and this generalizes the notion of the length, the Euclidean norm on Rn, because of course, if you take the absolute value of a real number and square it, it's the same thing as squaring the real number itself. Okay, the reason why we're taking the lengths of these complex vectors is because, the reason we're taking the absolute value of each of these complex numbers is because I want this norm in the end to be in R, if it's going to be some kind of length. So first, I take the absolute value of each component that returns a real number, then I square them, I add them together, I take the square root. Okay, but of course, this means just if you square both sides, that the norm of z squared is just the sum of the absolute values of each component. Again, this would also work over Rn, but now everything works over Cn. And then the length of a complex number squared is the same thing as the complex number times its conjugate. So this is z1 bar plus up through zn bar. So if you go back to this dot product, the dot product, we took the dot product of x with itself to get the length of x squared. What we weren't realizing because we were working over R was actually somehow the more natural thing to do is actually not to take x1 times x1 plus x2 times x2, etc., but to take z1 times z1 bar plus z2 bar, etc. And of course, if you're only worried about real numbers, when you conjugating a real number doesn't do anything. So you don't see the fact that you need to conjugate. Okay, so in other words, so if W and Z are two complex vectors, Cn, we want to define the product of these two vectors as W dot Z as something like W1 Z1 bar plus W2 Z2 bar plus Wn Zn bar. Right, so what I'm trying to say here is if we try to generalize the notion of the dot product to complex vector spaces, we'll realize that our definition in R wasn't seeing some slice of the picture. What it wasn't seeing was this need for complex conjugation. But this actually is a generalization of the dot product in R because you could throw in the complex conjugations to this definition if you really wanted to, right? If you wanted to, you could make this definition of the dot product of two real numbers, x1, y1 bar plus x2, y2 bar plus xn, yn bar. But since the y's are real numbers, it doesn't change them. Okay, but then one thing that you see here is that you're conjugating only the right vector. Right, so if you take z dot w, via this definition, you get z1 w1 bar plus z2 w2 bar plus zn wn bar. Now, multiplication of complex numbers is commutative, so this is w1 bar z1 plus w2 bar z2 plus wn bar zn. And this number is the conjugate of this number. So this is the complex conjugate of w dot z. Okay. But really, I'm being kind of bad here because I'm using this dot notation. This dot notation is not actually the notation we're going to use for these products. I'll introduce this notation in 1 second. But really, if I want to be precise, what I mean here is this will be the notation we'll use for products. Okay, so in a second, we'll introduce this notation. So you could just ignore the products for a second. Ignore this notation for a second. Okay, and note that this commutativity of the dot product is not going to be true for this product that we're on Cn. Right? The order in which you take the product does matter, but it only matters up to complex conjugate, which is the thing that we didn't see over R. Okay, so what we're doing is trying to generalize the dot product, but now that we've seen the complex numbers, we know the correct way to generalize. That's the moral of the story. Okay, so one thing that is true is we're still only going to work over R or C, because I still want, I mean, lengths basically must be real numbers, right? But there are lots of vector spaces that aren't just Rn or Cn. Right? For example, the space of all continuous functions on R. We saw that that was a vector space over R. Or the set of all polynomials of degree less than or equal to m. Or there's lots and lots and lots of different vector spaces over R that aren't just Euclidean space. So this generalization will now apply more generally than just dot products in Euclidean space. Okay, so we're going to fix the field to be either R or C, and we'll let V be a finite dimensional vector space. Sorry, just a vector space over F, actually not necessarily finite dimensional. And we're going to find the following: an inner product on V is a function that takes each ordered pair uv of vectors in V to a scalar. And the way that we'll denote the scalar is with these angled brackets, uv. Okay, so this will be like a dot product, right? What a dot product does is it takes two vectors, u and v, and it spits out a scalar. What an inner product will be is it will take two vectors in a vector space V, and it will return a scalar. The scalar, the notation we use, is this inner product of u and v. Okay, but of course we want it to have nice properties, so such that the following properties hold. For all u, v, w in V, and lambda in F. Okay, so what are these properties? The first property is a property that we call positivity. And it corresponds to this first dot product property we talked about. That if you take the dot product of a vector with itself, you always get a positive number. So what we'll say is that the inner product of a vector with itself has to be bigger than or equal to 0. But there's a bit of ambiguity here, because I just said that the inner product of two vectors, u and v, is a scalar, which means that if I'm working over C, this inner product could return a complex number. And then you could ask, what does it mean to say that a complex number is bigger than or equal to 0? So here, the convention is, if we're working over the complex numbers, then to say that lambda is bigger than or equal to 0 means that lambda is a non-negative real number. Right, so like 3 is a complex number also that's greater than or equal to 0. But I is not a number that's greater than or equal to 0, a complex number that's greater than or equal to 0. A plus I is not a complex number that's bigger than or equal to 0. Okay, so this positivity says really two things. It says, first of all, that if you inner product a vector with itself, you always get a real number. And then also that the real number will always be greater than or equal to 0. Okay, but in general, if you take the inner product of two vectors in C, you'll just get a complex number. Okay, the second property that we wanted to generalize is that the dot product is 0 if and only if the vector is 0. So this is what we'll call definiteness. So the inner product of two vectors of a vector with itself is equal to 0 if and only if the vector is 0. And then our inner products will be additive in the first slot. So let's call this additivity in the first slot. Okay, this is a generalization of this property, that for a fixed vector, if you fix the vector in the second slot, the map you get is linear. It's actually the next two properties. So additivity in the first slot means if you take the inner product of u plus v with w, it's the same thing as the inner product of u and w plus the inner product of v and w. So in the first slot, you can break up sums, although not necessarily in the second slot yet. Also homogeneity in the first slot. In other words, lambda u, the inner product of lambda u and b is the same thing as lambda times the inner product of u and b. Okay, so these two properties generalize this third property of, for a fixed vector y, the map taking x to x dot y is a linear map. Okay, and the last property of a dot product was that it was commutative. But we saw that actually you shouldn't demand commutativity. You should demand commutativity up to taking a complex conjugate. So this property is called conjugate symmetry. In other words, if you take the inner product of u and b versus the inner product of v and u, they're not equal, but they're equal after you take the complex conjugate on one side. Okay, so what we've just done is we just abstracted the properties of a dot product to just define what we mean when we say an inner product on B. An inner product is something that takes two vectors, spits out a scalar, and satisfies these 5 properties. Of course, now I owe you some examples, right? So of course, the first example is just the standard one. So I'll call it the Euclidean inner product. So if you ever want to specify that you're talking about the normal analog of the dot product on R or C, so the Euclidean inner product is given by, well, you take a vector w1 through wn, and you take the inner product with a vector z1 through zn. You just take w1 z1 bar plus w2 z2 bar plus wn zn bar. Okay, so when F equals R, this is the dot product. Okay, so the dot product is just this Euclidean inner product. Okay, second example. We can fix some positive real numbers. Let's say you fix, oh gosh. Okay, this happens, I think, when my palm recognition is wonky. Okay, let me try to. Okay, so if you fix n positive real numbers, then we can define a weighted version of the usual inner product. On f to the n. Okay, namely, if you want to take the inner product, two vectors like this, instead of taking the normal Euclidean inner product, you can just add a weight to the terms. Right, so e.g., let's say in R2, say, you can fix the vector, I don't know, 3, -1. And then you can define this weighted inner product of, say, x1, x2, y1, y2 to be 3x1, y1 minus x2, y2. Okay, so this generalizes the usual inner product. The usual inner product is where you take all the scalars to be 1. Here it's just like you're weighting different parts of the different components to be maybe different, have different weights. Okay, and then lastly, a very important inner product, which is also kind of going to be a new one, is if you let V, say, be all of the continuous real valued functions on the interval -1 to 1. And then we can define an inner product on V by the inner product of f and g is the integral from -1 to 1 of f of x, g of x, dx. Okay, so I guess I'm not verifying for you that it satisfies the properties, although I believe that you actually could because you know lots of properties of definite integrals from calculus. But just note that the elements of this vector space are, of course, continuous functions. So f and g here are two vectors in the vector space. They're two continuous functions. When you multiply them, you again get a continuous function defined on the same interval. And when you take the definite integral from -1 to 1, it does in fact spit out a scalar, right? It spits out a real number. So this takes in two vectors, two continuous functions, and spits out a scalar. Okay, and this kind of inner product is an extremely important inner product in analysis classes. Right, so I think if you talk to a functional analyst and you talk about an inner product, this is actually the one that they imagine. Or maybe they think of the dot product first, and this is the second one that they imagine. Oh, I guess I should also note that this is an infinite dimensional vector space. So here's a good example where generalizing the properties of the dot product can give us actually something new. Okay, so now we're ready to find what we mean by an inner product space. An inner product space is just a vector space with an inner product. So an inner product space is a vector space V with an inner product on V. Okay, so this notation means I'm denoting my inner product with angle brackets, and the dashes mean that I can plug in vectors into those two spots. Okay, so in the rest of this chapter, all of our vector spaces will be inner product spaces. It's a convention for the rest of the chapter. V will always denote an inner product space. And if V is finite dimensional vector space over F and no inner product is specified, we assume that we're using the Euclidean inner product. Okay, that is like if you're doing some kind of computation and you're asked to prove something about some kind of inner product, and they don't specify exactly what they mean by it, they mean the usual Euclidean inner product. Of course, when we prove theorems about inner products, it will hold for any inner product. Okay, so this is a new definition, right? I should say this is a new definition. It does generalize some old definitions, but since it's a new definition, that means that we have a new object, a new mathematical object to play with, which means that we should try to understand the basic properties first. Okay, and I think most math majors enjoy this kind of thing because at the very beginning, you only have the definition. It means that the proofs can't be too hard, right? If all you have is a definition, that's your entire toolkit for proving something. So you know that the proof must come from basic properties. Okay, so here's our first result on how inner products behave. So let V be an inner product space. Okay, then 1, for each fixed vector u, the function that takes V to the inner product. Okay, I should be really careful about my V's versus my U's. V to the inner product of V and U is a linear map from V to F. 2, if you take the inner product of any vector with 0 in any order, you always get 0, U and V. Okay, so 3, we assumed in our definition of an inner product that the inner product was additive in the first slot, but not the second slot. It turns out that actually that's a consequence. So if you take the inner product of U with V plus W, that's the same thing as the inner product of U and V plus the inner product of U and W. This is for all U, V, W in V. And then also we assumed homogeneity in the second slot. Sorry, in the first slot. It turns out that we don't get homogeneity in the second slot, but we get something a little bit different. If you take the inner product of U and lambda V, what you get is you can pull out the lambda, but you have to take its complex conjugate. So it's like you have conjugate homogeneity in the second slot. Okay. So let's prove these things. Proof. Okay, so for 1, maybe 1 is the most complicated looking thing. So I need to show that we have a linear map from that. If you fix a vector u, then the function that takes each vector to the inner product of that vector with u, that's a linear map. To show that a map is linear, you need to prove that it's additive and homogeneous. Right, what is the function? Just to be clear, the function that we're considering, t from v to f, takes little v and maps it to the inner product of v and u, but here u is some fixed vector that we fixed at the very beginning. Okay, so let's let v and w be two vectors in v. What do we need to show? We need to show that t of v plus w equals t of v plus t of w. We need to show that t of lambda v equals lambda t of v. But as usual, what I'll do is I'll just prove the first one. You can prove the second one. Okay, well, what is t of v plus w? T of v plus w is v plus w dotted, or the inner product of v plus w and u. But now you just use additivity in the first slot. This is v u plus w u, and that's exactly t of v plus t of w. Right, which is what I meant when I said that these two properties generalize that earlier property, the dot product, that if you dot with y, you get a linear map. Okay, 2. So you should do the homogeneity proof. What's 2? Well, since t is linear, the same t, we know that t of 0 equals 0. So this means that for every vector u, that's 0. But also by conjugate symmetry, the inner product of u and 0 is supposed to be the conjugate of the inner product of 0 and u, but we already saw that that's the conjugate of 0, which is just 0. Okay, so because of the first part, we know the second part. Okay, how much time do I have? Still got some time. Okay, so now we should think about how to prove the third part, right? Let me just. Okay, let me just start a new page. Third part, which by the way, just to remind you, is we're trying to prove that u of v plus w, we're trying to prove that it's additive in the second slot as well. This is basically just a computation, okay? So what we'll do is we'll just use conjugate symmetry to swap the two places up to a complex conjugate. Then we'll use the fact that's additive in the first slot, and then we'll flip back and use conjugate symmetry. That's the whole proof. So by conjugate symmetry, you can flip these at the expense of a complex conjugate. Right, but now this is the complex conjugate of a complex number given by an inner product, but the inner product is additive in the first slot. So this is just the complex conjugate of this big complex number. Now, a property of complex conjugation is that if you add two numbers in conjugate, it's the same thing as conjugating separately and adding. I guess this says that complex conjugation is a linear map. Right? At least it's additive. And then now you can flip them back by taking the complex conjugate. It's just if you conjugate twice, you get back to the place you started. Okay, so I guess I'm using two properties here that I didn't exactly prove or state. Here it's if you take the complex number z plus w and conjugate, it's the same thing as the conjugate of z plus the conjugate of w. It's a thing you could prove. Here, I'm using the fact that if you take the complex conjugate of a complex conjugate, you get the number you started with. Okay, there's actually a funny story. related to complex conjugation. Should I? I don't get to go on digressions as much when I'm teaching an online class, so let me just go on this digression. You can ignore this. You can ignore all the text in red if you want. There's a story of, I forget who. I should probably look it up. But there is a very famous mathematician, I think maybe even still alive or recently deceased. It's a relatively modern day story, who, whenever he was listening to a math talk, would always call out speakers if he thought that the notation they were using was bad. So, you would say, like, that's bad notation, you should use whatever other notation. So one time they I think they made a shirt. Maybe this was around his retirement or something. They made a shirt that said, like, that's bad notation. And they wanted to give it to him. By they, I mean, like, the other members of the seminar or something. So I think it was Ken Ribbit, some other famous mathematician, went and gave a talk and tried to get this mathematician to call out his notation. So what he did was he defined a complex number, lowercase c. This is a Greek letter, right? A complex number, lowercase c. And at some point, he took the complex conjugate of it, and then he divided by c. So this is the conjugate of c divided by c. But I think the guy, the sustained mathematician, didn't actually say that it was bad notation because the talk was something that he's sort of not an expert on. And so he didn't really feel comfortable making any comments. This is very common. If you're at a talk that you don't really understand what's happening, you don't ask any questions or make any comments because you figure the speaker knows a lot more than you do. So in the end, they just had to give him the shirt. But this is like hilarious notation. C bar over C. So this notation is not quite as bad, but okay. Anyway, digression over. Okay, part 4 is we're trying to prove, remember, that this thing is not homogeneous in the second slot, but homogeneous up to conjugating the scalar. But the proof basically goes as you would expect. You just take U and lambda v, its inner product. Then you could swap the locations up to taking conjugate. This is by conjugate symmetry. Then the inner product is linear in the first slot. So actually, let me actually do this step by step. This is just the complex conjugate of, if you pull out the scalar, it's homogeneous in the first slot. Then this is the product of two complex numbers. Then you can flip back using conjugate symmetry. Okay, so here I've used a property of complex conjugation, which is that if you take the product and you conjugate, it's the same thing as conjugating and taking the product. Yeah, but all the blue things, which I didn't state or prove, you can easily prove from the definition of complex conjugation. Okay, so these are the basic properties of inner products. You're homogeneous in the second slot. You're additive in the second slot. You're almost homogeneous in the second slot. And if you take the inner product with 0, you get 0. And that the fact that it's a linear map basically, I mean, this thing is a linear map just means that the first slot is additive and homogeneous. Okay, but back to our very, very initial motivation, which is that the dot product should know about lengths. We've just generalized the dot product to inner products, which is that the inner product should know about lengths. In what way should the inner product know about lengths? In the same way that the dot product knows about lengths. If you take a dot product with itself, you get the length of a vector squared. Similarly, if you take the inner product of a vector with itself, you should get some notion of length squared. That notion of length is what we'll call the norm. The definition. So if V is an inner product space, for a vector V and V, the norm of V is, okay, so the notation is, again, these double bars. And it's just the square root of the inner product of V with itself. Okay, so totally generalizes the notion of Euclidean norm on Rn and Cn, because if you just take the normal dot product or the normal Euclidean product on Cn, this is exactly the same way as we defined the norm of a vector, what I call the Euclidean norm of a vector in Rn. So inner products know about length in that if you inner product a vector with itself, it's the square of the length, the norm. Some basic properties about norms. Suppose V is a vector in V and lambda is a scalar in F. Then first of all, the only vector with norm 0 is the 0 vector. 2, if you take the norm of a scalar multiple of a vector, it's the same thing as the length of the scalar, the absolute value of the scalar, times the norm of V. Okay, so just a note that the norm of a vector is always going to be a non-negative real number, even if you're working over C. So this is always a non-negative real number, even if F equals C. Because by our definition of an inner product, if you take a vector and inner product with itself, you always get a non-negative real number. And then when you take the square root of a non-negative real number, you get a non-negative real number. Okay, so the norm is always going to return a non-negative real number, which is why I shouldn't be able to just expect to pull a scalar out of a norm. Because if I pulled out a negative number, or if I pulled out a complex number, it would no longer be a non-negative real number. But if you take the absolute value, then both sides of this, it's clear, will be a non-negative real number. Okay. Again, the proofs of these should be easy, right? Because we just, all we have is the definition of norm and the properties of an inner product. So by definiteness of an inner product, the inner product of V with itself is 0 if and only if V equals 0. Which means that the square root is 0 if and only if V equals 0. Right, and this is just the norm of V, the square root of the inner product with itself. Okay, for the second part, if you look at the norm of lambda V, well, if you square it, that's just lambda V inner product with itself. But now inner products are homogeneous in the first slot and then homogeneous up to a complex conjugate in the second slot. So you can pull out the scalars, except that you need to conjugate one of them. And then we said that a complex number times its conjugate is just the absolute value squared. Now you just take square roots. Okay, so let me just mention that what these proofs already show is oftentimes when you're working with norms, it's easier to work with the square of the norm, because the square of the norm is just the inner product of a vector with itself. So two things. One is that sometimes that's a technique you want to use, right? Work with the square of the norm. So you work with U instead of this. And sometimes it's enough to just prove something about the square of the norm. The second thing is you should always check to make sure that you've written down the definition correctly. In other words, you should always make sure that you haven't forgotten a square or a square root somewhere. It's a very easy mistake to make. Okay, I guarantee that some of you at some point in a proof will be very tempted to write this. It will naturally happen, trust me. You have to be hyper vigilant to remember that it's the square of the norm that's the inner product of the vector with itself. if you want the norm, you have to take square roots. Okay, well, I'm like 55 minutes in. We're like maybe halfway through 6A, but like I said, I sort of want to go slow through chapter 6 because it's kind of newer. It's the reason why I went fast to the earlier stuff. So why don't we stop here for today? And then next week we'll continue 6A and then 6B and 6C probably.